Okay, so yeah, feel free to start whenever you want to.
Yeah, well, first of all, I want to thank Zlatko for the invitation. Very glad to be here to talk about this work. So this will be following some recent preprint that we have on archive. So if you want more details, please go check it out. But yeah, so as Andrew said, I'll be talking about scars beyond PXP. And well, first of all, I want to put a bit of context. I know most of you are very familiar with these topics, but still, I think it's important to contextualize and keep the talk accessible. So I'll first do a bit of context, thermalization, non-thermalization, what I mean by this, then talk quickly about quantum scars, and then go into like the meat of the topic and this idea of scars in model with longer range blockade, and then go even further away from standard 1 PXP by going to higher dimension before concluding. So let me start with quantum thermalization. Usually when we talk about thermalization, we have a simple picture from everyday life. We have some system. Here it will be quantum because we do quantum. It's in contact with some reservoir at some temperature. And if you let things evolve, well, at late time, you expect your state to be at the same temperature as a reservoir. But it's important to keep in mind that the statement is more than this, right? It's not just the temperature of the system, it's the state of the system, because you don't just expect the temperature to be something, you expect it to be in a thermal state with something like a generalized Gibbs ensemble or something of the like. And so now we can ask, okay, well, now I only be talking about closed systems. So what do I even mean by thermalization? Our system has a thick boundary, it keeps energy, everything is unitary, nothing is lost, nothing is gained. So temperature is constant. So what exactly can we say? Well, we can actually say quite a lot. And the key for this is to split our system into a large subsystem and a smaller one. And then we can just think, okay, well, now my small subsystem is in contact with a big one, which is like a reservoir. At late time, they will have the same temperature, just means the system is homogeneous. But what is important to note is that then this small subsystem will also be in some kind of thermal state. So if I look at the local density, reduced density matrix, it'll be like a Gibbs state or something like this. And so that's what we mean by thermalization, that if we only look at constant quantity, everything will be the same as it was a thermal state. And so everything will just be given by the energy of the system, which gives it temperature. And so that's for dynamics, for long time. How do we understand this long time dynamic? Well, as usual, we look at eigenstates. And basically, the idea is that we have this kind of thermalization because of some property of the eigenstate. And that's the idea behind the eigenstate thermalization hypothesis, or ETH, which was put forward by Deutsch and Schrednicki in the 90s. And basically, the idea is simple. Like, okay, you have dynamics that leads you to thermalization at long time because the eigenstates themselves look like thermal states. So if I take some eigenstate at energy E, some local observable, well, this will just give me the same prediction as a microcanonical ensemble at the same temperature, plus some finite size correction. So essentially, it doesn't matter which eigenstate I pick. The only thing that matters is its energy. And then every local observable will just be a smooth function of the energy if I look at the eigenstates. And this is important for dynamics because if I look at some generic state, let's say a product state or something with local entanglement, it will be localized in energy. By that, I mean that the variance of the energy density will just go to 0. So if I look at the overlap of some generic state with the eigenstate, it will be, let's say, peaked around the energy expectation value of that state. And so if I let it evolve now, well, at late time, it's still the same distribution. So only the eigenstate in this regime kind of matter. But now at very long time, well, the energy spacing between all these states will be relevant. And so it's just a incoherent mixture of these states. And so the expectation value of the local observable is kind of the average over all these states. But this is exactly the microcanonical ensemble. So this is exactly the same value as the eigenstate. So essentially, we can understand the thermalization by the fact that the eigenstates are thermal. And if we want to avoid thermalization, we need to have non-thermal eigenstates. And the ETH also predicts a bunch of other things. For example, that away from the edges of the spectrum, the eigenstate have volume law entanglement entropy. So the entanglement entropy scales with the volume of the subsystem, and a few important things like this. And so now that we have the basis of thermalization, we can ask, well, in what case does the system not thermalize? Right? Are the systems that violate the ETH? And well, we all know some, right? And usually it works with extensively many conserved quantities. So quantities that commute with the Hamiltonian. And then if I pick a random eigenstate and another one of the same temperature, even if they have the same energy, they will always have some different quantum number. So they don't talk to each other and nothing looks thermal. And the simple case is integrability, where you can have basically anything depending if it's interacting or not. You can have area, log, or volume law state. It really depends on conserved quantities. And the other typical example is many-body localization, where due to strong disorder, you have local integral of motions that are essentially conserved. And well, this gives you, again, the same phenomenology. But there, because of this localization, all the eigenstates are area law, and so it's a bit simpler, let's say. But the main similarity between these two is that all the eigenstates violate the ETH. So I have no notion of whatever is thermal. There's nothing that is thermal, and so I can kind of have any dynamics. And of course, the question is that are there some other type of system that violate ETH, maybe in a more subtle way, where I still have some thermal state, but some non-thermal state? And well, this is exactly what these quantum many-body scars are. So this idea of quantum many-body scar is fairly recent. It essentially dates back to 2017, and it emerged from an experiment by groups at MIT and Harvard who were using Rydberg atoms. These atoms are essentially two-level system, which can be in the ground state and the Rydberg state. And here they looked at them in optical lattice, so in the 1D chain. And the Hamiltonian of this is fairly simple. So you have some free precession with some frequency omega, right? To just take you between the ground state and the Rydberg state and vice versa. So this is just some free precession of each integral atom. But now if two atoms are in this Rydberg state, they interact with each other with some van der Waals interactions that decay as distance to the power 6. And so this is an interacting system, right? You have some clear interaction, nothing is frozen, no special symmetry. So you expect things to thermalize. And what they saw when they're doing quench is that while most initial states thermalize, when they started from this Z2 state of alternating ground state, Rydberg state, ground state, Rydberg state, instead of thermalizing, observable, like this domain wall density, were instead oscillating for an extremely long time compared to the expected revival time. So this was kind of unusual, and this happened in the regime of the Rydberg blockade. So what do we mean by blockade? Well, it's some special regime of the parameters where the nearest neighbor interaction is extremely strong. It's like the dominant energy scale, much stronger than the flip term, which is itself much stronger than the subsequent longer range interaction. So essentially, we can forget about this longer range interaction because they're really minimal energy scale. But at the same time, this term, so the flip term, cannot create or destroy something of energy V1. It's just so much more energy that it's essentially conserved. And what this means is that to not add or destroy this V1, it means we cannot add or destroy neighboring excitation. And so these emergent blockades appear that if you have an excited atom in the Rydberg state, its nearest neighbor cannot be excited. You can excite atoms further away, but there is now some blockade radius, your radius 1, where you cannot add any more excitations. And essentially, the effective Hamiltonian in that case is the famous PXP model, where we still have the flip term, but it's now addressed with projectors on the neighboring atoms on the ground state. So basically, before flipping an atom, you check that both of its neighbor are in the ground state, and only if this is the case, you can flip it up, so you don't create neighboring excitation. And this omega here is now the only parameter, so I just set it to 1 because There's no need to keep it for simplicity. And so now that we have this simple model, we can look at kind of its property, and people did that after the experiment. So we can look at level statistics, and things look like Wigner-Dyson. So the system is non-integrable. There's no hidden symmetry or any kind of that thing. We can look at the dynamics, not just at observable, but at the level of the wave function. So here we look at this kind of return fidelity of the wave function over time, and we see that it has the same oscillation that observable, even in big system with 32 sites. And finally, we can check that it's not a finite size effect. So we can look at the growth of entanglement entropy in an infinite system using matrix product state methods. And what we see here is that the Z2 state in blue has much, much slower growth of entanglement entropy than other product states. So it is indeed special, and it's not just some finite size effect. And now that we've seen that the effects in experiment is real, we can try to understand why this is the case. And as for the ETH, well, we want to understand dynamics, we go to the eigenstates. So now the eigenstates here, what matters is the overlap between the initial state and the eigenstate, right? And if we look at it, instead of some kind of cone or featureless blob, we now see this kind of bands. And in particular, we see that we have one band of special eigenstate which have anomalously high overlap with the null state. And these states are almost equidistant in energy. And why that matters is because the phases then will realign over time because of this equal spacing. And this is why we get the oscillatory dynamics. And these states are not just special in overlap, they are also special in entanglement entropy. You see that they are at the bottom. And if you look at scaling, they have approximately log scaling of entanglement entropy instead of volume law. So these are actually very special states, and you can check that they do violate the ETH. But meanwhile, the other states, here in this kind of thermal bulk, these do obey the ETH. So we now have like some kind of weak violation of ETH, where most states are thermal, but you have a few sets of non-thermal states. And you will only see non-thermalizing dynamics if you start an initial state which has high overlap with these special states. And this is a phenomenon called so-called quantum anybody scarring, which has been called like this due to a similarity to the same phenomena in single particle physics. So this was 2017, 2018. And since then, people have worked a lot on these scars. They have cooked up quite a lot of new models. And I don't have time to talk about them, but most of them differ from PXP in the sense that they have exact scars. And by that, I mean that there is some kind of transformation when I can separate the scar subspace to the rest of the thermal states using simple transformation. And on top of this, most of them have oscillation due to some kind of additional symmetry. So this scar subspace has additional symmetry with respect to the full Hamiltonian, and it usually has an approximate SU2 algebra in it. So basically, you can understand these scars as like precession of a big spin, which is embedded in an otherwise thermal system. And well, this is interesting. And in fact, PXP has kind of the same thing. You also have an approximate SU2 algebra, but everything is approximate, including this separation. You cannot find any simple transformation that splits your scarred state and your thermal bulk. So PXP is still kind of special with respect to most of the model we know. And this is extremely relevant when it comes to theory of scarring, because people have not just come up with new scarred model, they come up with new theory to understand them. And there's quite a few of them relying mostly on symmetries and other special properties of the scarred state. And these all do and do not do a few things. What they do is that they unify scarring with conventional symmetries and Hilbert space fragmentation through the characterization of the additional conserved quantity in the scarred subspace. So scarring is no longer its own thing apart. It can be fitted with most of what we know. They also provide a way to construct scars model. by taking systems with many symmetries and breaking them in a specific way. These theories also provide a way to construct large families of models with scars from a single scar model by telling you what parameters you cannot change in which way to not destroy the scarring. But there are important things they do not do. Importantly, they do not give you a way to assess if a given Hamiltonian has scars. There's still no good way to do this except for trying quenches, doing ED, and brute forcing your way through. In particular, this theory do not have any predictive power for non-exact scars, as in the PXP model. So we can understand PXP, oh, it looks a bit like this model, so maybe we can apply this theory, but it has no, let's say, quantitative predictive power for PXP and other Rydberg atom models. And we understood this as kind of a gap. And so our question was like, has scarring in Rydberg chains been fully characterized? Like, we have found scars, people have studied these scars, but have people actually looked for more in this Rydberg atom arrays? Can we actually find new scars that people have completely overlooked? And that's why we started looking into these Rydberg chains with longer range blockade. So let me go back to our Rydberg Hamiltonian, because this is still the same, right? This model I will talk about can be engineered in exactly the same setup, just by changing the lattice spacing. So for PXP, we had this condition for the blockade. And this told you, oh, we cannot have neighboring excitation that costs too much energy, so I have a Rydberg blockade radius of 1. But I can look at other conditions, right? I can look at this. So by putting the atom close together, the nearest neighbor and next nearest neighbor interaction will be much stronger. And they can be both much stronger than the flip term. And what I tell you is what, okay, this prevents you from creating neighboring interaction excitations. And this prevents you from creating next nearest neighbor excitations. And so now basically I have a Rydberg blockade radius of 2. So around each excited atoms, on each side, I have 2 sides that I cannot excite. And the Hamiltonian, I get the effective Hamiltonian is just PPX right? I just keep adding projector to the left and the right. And I can keep doing this forever, right? I can just change the condition. And if omega is between VR and VR plus 1, I get a blockade radius of R. And it means I just have R projector on the left, R projector on the right. So it's very similar idea. Of course, the longer range term that we are neglecting will be like larger. So the approximation to the experiment is slightly worse, but it's still pretty good at this point. So we can really look at this model as experimentally relevant, and we can ask how they behave. Because if you just look at this and compare to PXP, well, they look almost the same. You can say, okay, well, if one has scars, surely the other must have. And people, of course, have looked at this. And as initial state, they've done the first thing to try, which is the equivalent of Z2 state in PXP, which is actually the state with the most excitation. So essentially, I put an excitation, and as soon as I can, I put another excitation. So basically, it has period R plus 1 and is, well, the equivalent of Z2 state in PXP. And this is pretty easy to do, like this system are easy to simulate. And if we do this, this is what we find. So here I'm just showing again this return fidelity of the wave function. And R is a blockade radius. So R equals 1 is PXP. We have nice scars. Okay, that's, we know. But as soon as we go away from this PXP case, so R equal 2, I just get thermalisation. And I see no change as I go to higher number. So as it stands, it seems that only PXP has scars, that PXP is very specific, and that these other Rydberg chains basically do not give you any scarring. And people have looked a bit more into them, and even if you scan, you brute force through the product state, you find no revival, no meaningful revival, nothing that compares to PXP. So is there really no scarring in this model? Well, to kind of understand this, we first have to understand why we don't see revival from these initial states. And of course, this is still interacting many-body system, right? So we cannot really understand dynamics exactly, but we can have some relatively helpful picture of what happens during the dynamics. So let's take the dynamics of the case where we know we have scars, the PXP model. We start from one near state, right? I have half of my Rydberg's atom which are excited. And if I let it evolve, after half a period, I will have the other half of my atoms excited. And if you just look at these two time points from afar, well, you could say, okay, but maybe I don't have any blockade. This is just the trajectory I would have for free precession, right? The blockade doesn't seem to do much. Of course, in reality, the blockade does much. It completely changes the trajectory in between this point. It changes the period. It affects like the fidelity. But if you just look at these 2 points, you might say, I can forget about the projectors. Now, okay, what about higher blockade? I take blockade range 2. I take my Z3 state, right? I put as many atoms as I can. So I leave a gap of 2 between them, but still I put as many. And now if my trajectory was without projector, I would end up in this state, right? Every spin, every Rydberg atom is just flipped. But of course, you see this is clearly forbidden. These two are forbidden. So now you cannot really forget about the blockades. And so, okay, well, maybe you won't have revival because it doesn't really behave like a non-interacting system. And why is that? Well, essentially, it's because the lattice is not bipartite. Because even though we represent it in a 1D chain, we now have interaction between next nearest neighbor, right? Because this atom and this atoms, they still feel the blockade, so they interact. So if instead of just drawing it as a 1D chain, I draw all the interaction, so all the atoms that interact with each other are connected, I get this instead of this simple 1D chain. And now I see I have something like triangles between, for example, these three. So my lattice is not bipartite, and I have some kind of frustration where this one and this one both want to get excited, but they cannot get excited at the same time because they communicate. So it's really some kind of simple frustration. So we really want a case where the lattice is bipartite, where I can have sublattice A occupied at first, and then sublattice B, and I just oscillate between the two. So how do we relieve this frustration? Well, we make the lattice bipartite again, but we don't want to just rearrange the atoms, right? Like this would be kind of stupid. Oh, I just take them further apart, I get back PXP, I get scarring, but that's changing the model. What we want instead is, instead of a normal lattice, we want an effective lattice, which is bipartite. And how do we get an effective lattice? Well, with effective particles. And there's two simple ways to do that. First one would be to do fractionalization, something like Majoranas or so. So each Rydberg atoms is now multiple particles. And the other way is exactly the opposite, is just doing coarse graining, where I take multiple sites and I group them together. And this is the approach we will have. And so basically, at first, we exactly do just that. We just do supersite, right, or super atoms with k/2 spins. So just a quick introduction that k/2 is used because later we will use k which is not integer, when k which will be odd, so k/2 will not be integer, so it's kind of easier to talk about k which will always be integer, and that's why you use k/2. But for now, it doesn't really matter. So we just group spin together. So let's see how this works for the simplest case. So blockade radius 2. So this is the chain we had, right? I showed it before where all the interaction are denoted. And let's just do some simple grouping. Let's group sites 2 by 2. The first two sites are grouped together. These two are grouped together, and we keep going like this. And now I can aggregate the edges, right? Like I don't care how many edges I have between these two. If I have edges between one in there and one in there, I add an edge between the supersites. And otherwise I don't. And if I do this here, I find that I recover exactly 1D lattice, like in PXP, with none of this next nearest neighbor. And in fact, you can simply do this with any of the high range blockade. The only thing you want is that, for example, this one must be long enough, big enough to act as the buffer because between its left and its right neighbor. And since the blockade range is R, each of these supersites must have at least R spins. So this gives you a first idea, a first condition of how you can group atoms together, the site of this grouping. But of course, now we have a 1D chain, but we don't really know what the dynamics on it is, right? Like, we want the dynamics to be like PXP dynamic on this effective lattice, which is bipartite, to get scarring. So what do we need for that? Well, we need the Hamiltonian to flip this supersite between some ground state and some excited state. So they mimic two-level system. And we need the same kind of PXP blockade. So I want to be able to have two unexcited state next to each other. And excited and non-excited state must be able to be between each other. So we really want to just mimic PXP with this. And well, the best way to do that is just to say, well, okay, then my non-excited supersite will just be a collection of non-excited Rydberg atoms. That's really the simplest way. And then whatever I put next to it, the blockade will never kill it. So I'm fine with that. So I define that my non-excited supersite are just k/2 ground states, which are denoted by 0. And then since we want the Hamiltonian to take me from this to the excited state, I define just the excited state by the action of the Hamiltonian on my non-excited state. And what this gives me is just one excitation, because that's what the Hamiltonian does, but it's now spread evenly between all sides on my superatom. So essentially what I get is just a W state on these k/2 sides. So if I have 2, it's just a bell pair. In general, it's a W state. So are we done? Well, no, we have done only half of the work because we still want to be able to go back from the supersite, which is excited, to the supersite, which is non-excited. And in order to do that, we want the Hamiltonian to only remove these excitations. So we want this supersite to only have at most one excitation, because otherwise the Hamiltonian can just keep adding excitation and our mapping to a two-level system is dead and nothing happens. And the way to do this is just to keep this supersite small enough so that it can be at most one excitation. And it's pretty straightforward to see that for that to happen, my supersites must have at most R+1 atoms. And if I have this, so that my supersite at R or R+1 atom, then in theory, I have some approximate mapping to PXP with this effective supersites. And well, if we know it's like PXP, then we know we need to start from the null state. So I just prepare some initial state with unit cell size k, where the first half is non-excited and the second half is excited, so in a W state. And I keep this constraint, so k is 2r or 2r+2 for the mapping to work. And if we now look at the dynamics, it looks a lot like PXP. So this is again the fidelity. The blue and green lines denote these k states in system with blockade range 2 and 3. And you see that, yeah, you have these oscillations a lot like PXP. And if you check the product state with the same period, so like this Z6, you see that you have thermalisation as expected. So we have now found some state that revives, but these are not product state. And we can see that the same phenomenology as PXP works, and it also works for the eigenstates. So here I'm plotting the overlap between the eigenstates on my k initial states. The left is blockade range 2, right is blockade range 3. And you see, as in PXP, you now have these equally spaced states with very high overlap. And well, the entanglement entropy here is lower, here it's not, but that just depends on the number of states in the tower. And the agreement with PXP is not just qualitative, it is also quantitative. So if we take PXP, we know that the number of scarce states is just a number of sites plus 1. And here, the number of scarce states is number of supersites plus 1. So we really have this approximate mapping to the PXP that takes us back to a bipartite lattice. And then we can ask, okay, well, that seems to work well, but can we go beyond this supersite? Is the picture a bit more complicated than this? And actually, yes, because we can take a unit cell, which is now odd. And it's easy to see that the supersite mapping breaks down because we cannot really divide this unit cell into 2 equal half, one occupied, the other non-occupied. But what we can do is we can make these two supersites overlapping, with the middle side being parts of both. And now the mapping to PXP kind of breaks down, but the picture is still similar. And now our case state, right, our initial state, which is supposed to mimic the null state, looks a bit like before. So the first half is non-excited, the later half is excited, and now the middle one is half excited because it's part of both. So it's within the W state of the later half, but with a prefactor which is smaller. So if you look at occupation density, 0 occupation, maximal occupation, and somewhat half occupation. And well, this is a pretty simple ansatz, but it actually works quite well. So here you can see the result for fidelity aggregated over many, many different systems. So blue curves are k equals to r, red orange is 2r plus 1, so the odd case, and the green one is 2r plus 2. And the shading just indicates the blockade radius r. So here we have like 18 curves, and they all basically show the same scarring. And you see that in orange, red is not worse, and if anything, almost better than the even k case. And so we really have scarring for all these blockade radius, and in each case for 3 different states. And once again, we can see the approximate mapping to PXP by noticing that these all have the same period, which is the same as PXP, if we rescaled the time by the effective PXP matrix element. And so in PXP, the matrix element between the ground state and the excited state is just 1, because we set omega to 1. But now here, the matrix element between our unexcited supersite and excited supersite is square root of k over 2, just because we have k over 2 excitation. And so if we just do this simple rescaling, we find a very good match in frequency. And so let me quickly summarize the results for this system. So for arbitrary blockade range, we find 3 reviving states, which correspond to different families of scar. So for each of these reviving states we find, for each of these case states, we have their own set of scarred eigenstate, their own subspace. And once again, these scars are not exact, so they are not completely decoupled from the thermal bulk, but approximately so. And that makes the scars still good, but much, much harder to detect than exact scars. And the fact that we have 3 different reviving states is also true for PXP. So for PXP, we have scarring from the k equal 4 state, which was never found in the literature despite 50 plus paper on the model. People knew about Z2, they knew about Z3 and its entangled counterpart, but there was no result showing that some state with unit cell 4 was also revived. And what this shows, in fact, is that PXP is not a special case for which scarring emerge because it's extremely fine-tuned. Like now we know that PXP has 3 reviving states just like the other models. Right? So this was previously what was known. We have Z2 and Z3 for PXPs that were scarring. The rest was believed to be not scarred. And now if we look at all blockade radii, we have at least 3 families of scars, even more in larger model, although these are much worse. So what we have shown is that all one-dimensional Rydberg chains in some blockade regime have scars, but the cost is that to probe some of them, you need entangled initial states. And now the natural question is, okay, well, we essentially solved the 1D case. Can we go to higher dimension? And now these are some new results that are not in the preprint. And I will go relatively quickly over them because the story is kind of the same as in 1D, it just has a lot more possibility. So what's the status of scars in 2D PXP? Well, people have looked at 2D PXP. They actually, the group of Misha Lukin, they have looked quite a lot in experiment at these lattices of Rydberg atom in 2D, and they found scars in many, many of them. And essentially, the conclusion was that for any bipartite lattice in 2D, they see scarring if they start in the nail state. But for all the non-bipartite cases, they do not see any scarring. Of course, they have not tried all the different initial state, but they tried the obvious candidate for initial state, and they saw no scarring. And so we asked the same question. Is there really no scarring, or is it just that they didn't try the right state? And well, if I'm presenting this to you, you can imagine that it's because we indeed find scarring. So let's look at a few examples. The first one is a square triangular lattice, which is just this lattice made of, well, square of triangles, as the name indicates. And as soon as you have triangle, you know it's not bipartite. And if you look at any kind of product state, you don't get revival. But now we can do the same as before. We group sides together, and we group them with these dimers highlighted in red. So these dimers only have two atoms between them, which talk to each other. So the mapping to the two-level system is okay because they can be non-excited or in a bell pair. So that works. And if we now look at the effective lattice of these dimers, we find that it's just a square lattice. So they do live in a bipartite lattice. So at first glance, this seems to work. And we can make a nail state of this, right? We can put half of the dimers into some excited bell pair state and half of the other one on the ground state. And well, of course, this is a bit more tricky to simulate, but we can still do ED with relatively large system with 36 spins and 400,000 states in the Hilbert space. So the finite size effects are not that strong. And we find the same that in 1D, meaning our diamond nail state that I showed you on the slide before shows extremely clean revivals. Meanwhile, all the product states that we try directly thermalize. So this non-dimer is just, we pick our dimer state and we just pick, instead of bell pair, one state in each dimer. This is just the all-down state with no Rydberg excitation. And this is a state with maximally packed excitations. And all of this show the same behavior, they just thermalize. So what we see here seems to be genuine scarring and not any kind of finite side effect. And in fact, we can once again go beyond dynamics to go to eigenstates. We can diagonalize the fully symmetric sector, which has 6,000 states. And first of all, we find it's chaotic. So again, it's not some hidden symmetry, it's not some integrability, it's really scarring. And we find the same behavior as in 1D PXP with this towers of state equally spaced in energy. And what is more interesting is that if we look at the entanglement entropy of the eigenstates, we no longer have clear outliers like these, at least for this cut, because now the cut is a problem. It's a question of which cut we should take. But for the cuts we looked at, we find that the scar's entanglement entropy is very close to the thermal one. And so this means you will never be able to identify this state just by brute force. So you really need to know what you're looking for and how to probe it to find these scars. So that was a square triangular lattice, but we look at a few other ones. For example, the Ruby lattice, which is another of this lattice with triangle and squares. So again, you have triangle, it's not bipartite, but we can do the same type of coverings. But now instead of just doing dimers, we can actually do triangles. And well, these triangles can have at most one excitation. So the mapping to an effective two-level system works. And the effective lattice of this triangle is just a hexagonal lattice, which is bipartite. So we found a potential scarce state. And in fact, there's another covering, which is a bit less trivial. It's the same covering, but we now split the triangle between a dimer and a single site. Well, the single site are two-level system. The dimers are effective two-level system. And the effective lattice is this weird doubly hexagonal lattice that is weird, but is still bipartite. So now we have our two candidate initial state. We can look at dynamics. And the triangle covering works quite well. The mix between vertex and dimer is a bit worse because the dimer oscillates at the frequency that is square root of 2 faster than the single excitation. So you get some kind of mismatch between them, but still, both of these states show clear revival, much better than whatever maximum occupancy state you try. So for some of these non-bipartite lattices, we seem to indeed find scarring, and pretty convincing scarring at that. And we can ask if, as in 1D PXP, we can also find more scarred states in bipartite lattices, and if any of them could be interesting. And well, if we look at bipartite lattices, there's the simple example of the square lattice, which is the simplest generalization from 1D. And then, well, we can just do dimer coverings as before. And the effective lattice is just a smaller square lattice, so it's still fine. And we can use the symmetries of the model, so translation and rotation, to find similar states. So here we have horizontal stripe, shifted horizontal stripe, vertical stripes, and shifted vertical stripes. And these all give different initial states which have very small overlap in large system. And well, in blue is just the usual null state, and in red are these new scarred state. And the fidelity is worse, but it's still clearly scarring. So we went from 1 scarred state to 5. That's already quite good, but 5 is still quite small with respect to the size of Hilbert space. So can we get more? Can we get many, many scarred states in some of these models? And the answer is yes, but for that we have to look at the hexagonal lattice. So the hexagonal lattice is bipartite, so you can make the normal null state, but you can still do these dimer coverings. So here you have this vertical stripe, for example, and well, the dimers, effective two-level system, that's fine. And if you look, each dimer has 4 neighbors because you have an effective square lattice. So you get 1 more scarce state. Okay, that's pretty good. And you can find more in a way that is not just the symmetries of the Hamiltonian. You can find scarce state in a way that scale with the size of the system. And for that, we need to start from another of these scarce states, which I call this zigzag state because we have this zigzag patterns of dimers. So this state is again some kind of square lattice. But now we can modify it in a way that is not just a symmetry of the Hamiltonian. We can modify it in a semi-local way. So we can go from it to this one. And what has changed between them is just these 2 lines next to each other. Before you had the dimers on the left, top left, and now it's on the right part. So you can shift the line, and you could shift any line. So already, okay, you have a number of scarce states that scale linearly with the number of these lines. But in fact, it's much more than this, because now you can shift this line and the line on top. So here we have shifted these 2 and these 2. And you can see that the 2 shifting cancels out in the middle, but this one is different from the initial state here. And this one is also different from the initial state here. And so basically for each of these neighboring pair of lines, we can decide to shift them or not in an independent way. And so in the end, what we get is a number of scarce states that scales exponentially with the system size, or at least with the size along y. And so here the number of this place where we can shift is just 2ly. Well, ly is a number of unit cell along the y direction. And we have this -1 because if you shift all of them, it's like you're shifting none of them. So they're not all independent. But still, we get something that scales exponentially with system size. So we went from 1 to exponentially many quantum scars in that case. And as soon as it's exponentially many, you can ask if it starts to modify the general properties of the system, not just if you start from this initial state, but some more interesting thing like infinite temperature properties. And of course, we still want to check that this revive. So we did some numerical simulation in a small-ish system. And as in the other bipartite case, the actual null state is the one that's reviving best. But you see that this vertical stripe and these zigzag patterns also give you clear scars. So this model is particularly interesting, and we're currently looking into the infinite temperature properties to see if we see traces of scars in them because we have so many scar states. So that's it for 2D. This is still a work in progress, but I think it's quite interesting. And so it's already time for me to conclude. So overall, I've discussed quantum many-body scars, which are kind of a novel way to evade thermalization in quantum system, distinct from integrability and MBL. And in our work, what we have showed is that there were still many, many undiscovered scar trajectory among Rydberg system, whether it's chains or 2D. And the important part is these cannot be detected from product states, and instead require a small amount of local entanglement to relieve this frustration. And that's why they have been undetected for so long, because they are much harder to find both numerically and experimentally. And our approach is relatively simple and can be generalized to higher dimensions. So you could go to 3 or even higher dimension. It just becomes a bit harder to find whatever covering, so what your supersites are, as your lattice gets more and more complex, but there's no theoretical barrier here. And our findings can also be readily tested in Rydberg atoms array. As long as you can prepare bell pairs at places you want, then you should be able to find the scar state and see them experimentally. And overall, our results suggest that scars could be much more prevalent, so not just in Rydberg atom arrays, but maybe in other platforms. And it's just that the one we saw now in experiment are just easy to see one because they rely on product states. And that there could be many more that rely on slightly entangled state and so have never been measured just because they are hard to find. Finally, I'd like to finish on an open question, because I've shown you all these systems that do have scars. And the question we still want to answer is, actually, can we find such scar for all lattices? Is there some criterion that your lattice has to fulfill in order to have scars? And this is still an open question, and we're working on it. And hopefully, I'll be able to present the answer to that in a few months or a few years. And with that, I would like to thank my co-authors. So Aaron, who was a PhD student who did most of the simulation, and Marco, who was at ISTA and is now at TUM, and Maxime for doing a lot of the guidance and mentorship. And I remind you that most of these results, at least the 1D, are in our preprint that you can check now on arXiv. And I thank you for your attention.